Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 1 Organic Chemistry 2. This is an English version for my lectures. We will start the title with EN. In chapter 1, we will cover conjugated bisystems and pericyclic reactions. So we will talk about classes of dienes, conjugated dienes, molecular orbital theory, electrophilic addition, thermodynamic control versus kinetic control, introduction to pericyclic reactions, Diels-Alder reaction, molecular orbital description of cycloadditions, electrocyclic reaction, and sigmatropic rearrangement. Classes of dienes, we have three types. 1,2-diene, we call it cumulated dienes, where we have the central carbon sp hybridized, and the two terminals are sp2. So their planes, these two double bonds, their planes are perpendicular to each other. We have also conjugated diene, where we have sp2, 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 sp2 hybridized. So this single bond formed by the overlap of sp2, sp2, and since the sp2 orbital is shorter than sp3, scientists explain the length of this bond is shorter than the carbon-carbon single bond because of the hybridization of these two carbons. We have also isolated dienes. The pi bond are separated by two or more single bonds. So we have here sp2, this one is sp2, and here sp2, sp2, separated by sp3 hybridized carbon. Nomenclature of polyene, that it's very similar to the nomenclature of alkene. We have to choose the longest chain incorporating both double bonds, and then number them to indicate the position of functional and substituent groups. If necessary, we have to write prefix cis trans or EZ to indicate the geometry around the double bond. For this compound, its longest chain is 5 carbon, so we have benta, its here is 1 and here is 3, so it's 1,3-butadiene. Since carbon number 1 carries two hydrogen identical groups, we don't have cis trans or EZ. So the geometry will be the 1 on 3 and 4, and that will be, here we have here, this group is senior methyl over hydrogen, and here we have this group senior over hydrogen. So these two groups are on opposite sides, so it is E. So the name of this compound will be E benta 1,3-diene. Let's look at this one. The longest chain will be the one carrying double bonds, and we count them shortest to the double bond, so it will be 2 and 4, so it's hepta 2,4-diene. Let's talk about the geometry in here on 2 and 3. So here we have this is senior than this, and the whole senior than this. The two groups are on the same side, so it is 2z. What about the one between 4 and 5? 4, of course, this group is more senior than this, and here this one is more senior than hydrogen. So these two groups are on the opposite sides, so it is E. So naming this compound 2Z4E hepta 2,4-diene. Let us look at this molecule. Here we have the long chain 5, again on 1 and 3. So it is benta 1,4, sorry, it's benta 1,3-diene. And to look at, one has 2 hydrogens, so there is no E and Z or cis and trans. We look now to the carbon number 3 and 4. On 3 we have this senior than hydrogen, and here on this carbon we have brom senior than CH3, and the two groups, senior groups, are on the same side, so it is Z. So this molecule is Z, 4-bromo benta 1,3-diene. Let's look at this compound, long chain, number here from 1, 2, 3, and 4. So it is hepta 1,4-diene. One more time, this hydrogen, this carbon carries 2 hydrogens, so there is no E and Z. For the double bond 4 and 5, we have here the senior group here and here. They are on the same side, so it is Z. And this is non-conjugated diene. This is 1,3-cyclobentadiene, or we can call it cyclohexa 1,3-diene. Here is 1, 2, and 3. For this one is cyclohepta 1,4-diene. If we call it 1, 2, 3, and 4. And again, this is non-conjugated cyclic diene. According to the general methodology described in the current version of Nomenclature of Organic Chemistry, IUPAC, the Blue Book, in 2013, we have to select, as we said before, has a great number of the multiple bond. The chain with the highest greater number of the multiple has the lower locants for endings or prefix that express changes in the level of hydrogenation, where is a double bond and where is a triple bond. Therefore, the correct name for the compound here is 4-ethinyl hexa 1,4-diene, not 3-hexylidine hexa 1,5-diene. See, we can select this chain, and this will be carbon 1, 2, 3, 4, 5, 6. Right? And the name in here will be 4-vinyl or ethinyl hexa 1,4-diene. But we can still look at 6 carbon this way, but if we select this chain, it will be 1, 2, 3, 4, but double bond here is 5 and here is 6. So in the blue one, that's 1,5-diene. In the red one, it's 1,4-diene. Which one you select? You select the shortest. You select the shortest. So we select this one is the correct name. Suggest names and or draw structures as appropriate for the following compound: cis 1,4-dibromo 1,3-butadiene. So what we have to do is just write down the 1,3-butadiene or buta 1,3-diene. Okay, here we are. Then 1 and 4 dibromo, so we have to add on 1 and 4 the bromo. Then we have, it's kind of going backward, cis on the double bond. So we have to have the 2 hydrogens to be on the same side, to be cis, okay, and then the other 2 hydrogen also, you write them or with the structure to have them on the same side to cis. So this is the structure of this compound. To name this compound, this is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Okay, so that is these 2 groups are opposite side, so it will be E 2,3 dimethyl benta 1,3-diene. Draw cis 3,6-dimethyl 1,4-cyclohexadiene. First, I'll draw 1,4-hexadiene, 1 and 4, double bond in here, and then we go on 3 and 6. On 3 and 6 we have dimethyl cis to one another, so means that they are on the same direction. So if we draw them below the plane, they are correct. Both of them up the plane is correct, and this is the structure. How we can prepare this conjugated diene? It's exactly the same methods we used for the preparation of alkene. Either dehydration of alcohol or dehydrohalogenation of alkyl halide. So if we started with 2-methyl bent 4-ene-2-ol, dehydration in acidic medium, potassium hydrogen sulfate and heat, we eliminate water and obtain 4-methyl penta 1,3-diene. If we start with 4-bromo, 4-methyl bent 1-ene, and dehydrohalogenate that minus HBr using base like potassium hydroxide or tertiary butoxide, potassium tertiary butoxide, we get the 4-methyl benta 1,3-diene. It's better to use a bulky base to avoid any SN2 reaction. We can compare the relative stability of conjugated and isolated dienes by comparing their heat of hydrogenation. Here I select compounds with 5 carbons. The first one here is 2-bentene or bent 2-ene, bent 1-ene in this one, and here is 1,3-bent diene, 1,4 or bent 1,4-diene, and here is bent 1,2-diene. If we hydrogenate these compounds, all of them will end up to provide us with pentane. Well, here is a double bond at 2 position, has 2 substituents, so it is disubstituted. It released only 28.6 kilocalorie per mole, while when we have it 1 bentene, it releases 30 kilocalorie per mole, which means it's higher in energy and less stable. We notice that this compound is mono substituted in. When we have here diene, double bond in here and double bond in here, here is disubstituted and here is mono substituted, we are expecting that it releases 58.6, which is the sum of this and that, but actually give only 54, not 58.6, which means that it's lower in energy, it's more stable, and the difference we call it stability energy, okay, or heat of stability. When we have this one-four bent diene, it's actually giving twice the value of the bent 1-ene, 30 times 2, which there is no stability in this system. For the 1,2, the energy of this molecule releases 70 kilocalorie per mole, which means that it's less stable than the sum of 2 double bond, which means it's less stable. Recall, increased substitution increases the alkene stability. But why is that? Because what we call it hyperconjugation. Hyperconjugation, bonding interaction between the filled CH orbital and the vacant neighbor bi-star antibonding orbital. So if we have here sigma bond, 2 electrons, and we have on these 2 carbons we have anti-bonding. Okay, so this anti-bonding orbital is empty. Delocalization of these two electrons between the CH bond and the empty orbital, delocalization makes stability. We call that hyperconjugation. Conformation of 1,3-butadiene. We can have that structure in two forms, either single bond here and single bond here, rotation about this single bond gives S cis, where the dihedral angle between the two double bonds is 0, and S trans, where the dihedral angle is equal to 180 degree between these two double bonds. Of course, the trans is more stable because in cis, which is less stable, we have here steric effect. So at room temperature, these two conformers rapidly convert one another, moving more toward the trans, which is more stable, and establishing equilibrium. The activation energy of conversion from S cis to S trans is about 3.5 kilocalorie per mole, 15 kilojoule per mole. Looking for the molecular orbital, if we have two electrons in b orbital adjacent to one another, they can form two molecular orbitals, pi and pi star, and the two electrons, of course, occupy the pi orbital, and the pi star will be empty. In the 1,3-butadiene, when we have 4 b orbital, 4 electrons, we will have 4 molecular orbitals. 4 molecular orbitals, psi 1, psi 2, psi 3, psi 4. Lower in energy will be filled by 2, another 2. So we are done. And psi 2 will be the highest occupied molecular orbital, and psi 3 will be the lowest unoccupied molecular orbital. The lowest energy, psi 1, exhibit double bond character at C2, C3, while in the second one, psi 2 does not. Because of the presence of a double bond character between C2 and C3, which is shorter, that explains why the C2, C3 lies between the bond lengths of single bond and double bond. The reactivity of conjugated polyene could be understood by focusing on their frontier orbital اللي احنا بنقول عليها اللي هي الهومو highest occupied molecular orbital واللومو and LOMO the lowest unoccupied molecular orbital, discovered by Kenichi Fukui in 1954, and he obtained Nobel Prize in Chemistry for that, for his contribution in 1981. For the hexatriene, we have 6 electrons, b electrons, so we have 6 molecular orbital, psi 1 till psi 6. Again, we have 6, so here is 2, here is 2, here is 2, makes psi 3 HOMO, highest occupied molecular orbital, and psi 4 lowest unoccupied molecular orbital, LOMO. If we shine this molecule with light, one electron will move from psi 3 to psi 4, and psi 4 will be HOMO, and psi 5 will be LOMO. And we will get to that, explain that later in more detail. Electrophilic addition of diene. If you have 1,3-butadiene, reacting it with HBr at 0 degrees Celsius, we obtain 70% yield of 3-bromo but 1-ene as 1,2 product, 1,2 addition product, and 30% of 1-bromo but 2-ene, that's 1,4. We add here hydrogen, we add here Br, and that's what we call 1,4 addition product. Mechanism for that, the 1,3-butadiene, we have looking for this one. This is alkene, and this carrying more hydrogen, so HBr, according to Markovnikov rule, the first step is addition of H plus, so that will be CH3, and this carbon will be the carbocation. Because this is allylic carbocation, resonance structure with this carbocation, okay, will be established. Then Br minus then can attack with the red line, red arrow to this carbon, or the blue arrow to this carbon, forming the product 70 to 30%. Now, if we do the same reaction but at 40 degrees, we obtain the 3-bromo but 1-ene in 15% yield, while 1-bromo but 2-ene in 85%. Again, why is that? See, getting to this step, the formation of the resonance structures, carbocations, at a low temperature, the activation energy needed for this one to form 1,2 activation energy is small, and that's why we get more yield of 1,2. At 40 degrees, we can have this and that, both of them. But at 40, this can go back to the intermediate, and then again comes with a higher temperature to the more stable thermodynamically 1,4 adduct. Okay, and stop there. Some of them will be form 1,2, but again we'll go back and then take higher energy and then get to the more stable 1,4 adduct. Okay, so 1,2 we call it kinetically controlled, while the 1,4 adduct we call it thermodynamically controlled or thermodynamic controlled. To double check our understanding on this thermodynamic control versus kinetic control, let's solve this problem. Bromination of 1,3-butadiene at 60 degrees Celsius gives 3,4-dibromo 1-butene and 1,4-dibromo 2-butene in 10:90 ratio, whereas at minus 50 degrees Celsius this ratio is 60 to 40. Explained by mechanism. As we understand, the first step will be electrophilic addition, where the double bond attacks the partially positive bromine, and here is partially negative, and will kick out Br minus and form a carbocation, allylic carbocation. It resonance between two structures. These are the two resonance structures here, resonance structure. The Br minus then attack in second step either in a blue arrow or the red one to form the 1,2 adduct and 1,4 adduct in 60 to 40. at minus 50 degree Celsius, these two compounds are stable and do not undergo dissociation. So there is no reverse reaction. At 60 degrees Celsius, these compounds will dissociate back to the intermediate allelic and get activation energy to form the thermodynamically more stable product 1,4 adduct, and keep going forth and back and forth until it forms 90% 1,4 adduct and just only 10% 1,2 adduct. So warming to 60 degree provides enough energy to regenerate the allelic cation. At this temperature, the products and the cation are in rapid equilibrium, and the product distribution is under thermodynamic control, reflecting reactive stability. That 1,4 dibromoisomer is more stable, it is more substituted alkene than the 3,4 dibromoisomer, and the observed product ratio changes to 10:90 ratio. See you next lecture. Bye.